Okay, welcome to part 2, chapter 29. The hope was that you viewed the couple of videos on magnetic fields generated by current carrying wires. That'll give you a good phenomenological view of what Ørsted viewed in 1820. So again, 1820. Ørsted, Hans Christian Ørsted, did an accidental experiment, and so let's see this experiment. Let's see what happened here. So here's a wire connected to a source of electromotive force. Within that wire is going to be established a current. So you're going to have a current in this wire. And what Ørsted noticed is that when you brought a compass near that wire, the compass responded. So, and you hopefully saw what happened to the compass needles when I turned the current on and off. So let's take a look at this with a little more depth, right? Still no mathematical depth, but let's pretend that we look at this wire on end. So here's the wire. And say I rotate this wire so that the current is coming out. Okay, so current is coming out of the plane of the paper. Okay, and so what Ørsted noticed, and what you noticed, I hope, was that if you looked at concentric circles around this wire, something like so, what Ørsted noticed was that the compass needles, right, looked something like so. And I'm drawing these arrows such they're getting smaller as you move far away. That makes sense, actually, because you would imagine that the magnetic field generated by these wires is going to decrease as you move away from the wire, and we'll get more into that in a bit. And so if he also noticed that if you were to reverse the current, that is, if you had current coming out, right, current out of the plane, current going in, current going in, current into the plane of the paper, then likewise we have these concentric circles around the wire, and what he noticed was that the compass needles then switch the directions. Okay, something like so. I'm not going to draw all of them again. Okay. So this circularity of magnetic field is clearly very different than what we saw in a line of charge, right? Remember, just by contrast, if we were to go back and look at a line of charge, right? So look at a material that has positive charges embedded in it, right? So these are electrostatic, right? They're not moving. This is not a current, right? These are charges that are stationary and embedded in this wire. You will recall, and we spent some time dealing with this, that the electric field is radially symmetric out from the wire. So this is what it would look like from a side view. And if we were to look at it on end, right? So if we were to look at it on end, positive charge right down the barrel of that wire, then what we would see is electric field, right, coming out cylindrically symmetric. Right, so these are electric field lines. These are electric field lines. Okay, so very different than this circular nature of the magnetic field, right? So a couple of things going on here, right? So what you want to know is what is the magnetic field related to, right? So so you can clearly probably figure out that it's proportional to I, and it's probably going to fall off as you move away. So it would be R to the nth power, where n is yet to be determined. And I'll give you the answer up front. So the magnetic field then is going to be mu naught over 4 pi. The current, I guess the current will make a lowercase I, and you'll see both, I over so I guess when this smoke clears here, hang on a second. So this is going to be 2 pi. It's going to be 2 pi times R to the first power. So that's how the magnetic field is going to go as you move away from this current carrying wire. Okay, so that's interesting. We're going to derive this either in this little chat or in the next one. So we'll derive this, and we'll need a little calculus, which will be kind of nice. But so anyway, that's where we are now. We need to talk a little bit about the directions here, okay? The directions of the magnetic field. And so I'm going to redraw this wire down here, okay? Just so we don't complicate the picture above. Now remember, it was connected to a source of EMF. I guess I should have put that up here as well, source of EMF. And that's going to establish a current in this wire. If we were to look at this wire on end, such that that wire is oriented in a way where the current is coming out at us, we saw above that the magnetic field now is going to be oriented this way. It'll be tangent to these concentric circles, right? So tangent to these concentric circles. And its strength will decrease as you move farther and farther away from the wire. So now if if we were to draw a line right down, smack down the middle of that wire, and so now, right, so if again we were to orient this wire back, right, come back to this orientation, okay, so again, if we were to look at that, then magnetic field would be coming out at us above this wire. And it would be going into the plane of the paper below the wire. Now that takes some three-dimensional thinking, and we need a new right-hand rule. So, so the way this goes is the following, right? So the right-hand rule for this, which is different than the right-hand rule that we had for charges moving in magnetic fields. This time we start with our thumb. So we start with our thumb of our right hand. We place our thumb in the direction of the current, we curl our fingers, which now are in the direction of the magnetic field as we curl around the wire. Okay? So again, if I were to reverse the current in the picture above, that is, the current is going right to left instead of left to right, then all directions would be changed. Okay. So now let's begin to derive the equation for the magnetic field for a straight line current carrying wire, which I told you above was mu0 over 2 pi I over r. Now what I didn't tell you there was what mu0 was. Okay, so mu0 is called the permeability of free space, or what's sometimes called the permeability of vacuum, and it's equal to 4 pi times 10 to the negative 7 Tesla meters per amp. Now those units make sense, right? Because if we were to look at this equation, then B is going to need to be in units of Tesla, current is in units of amps, and the distance away from the wire is in units of meters. And so for both sides of this equation to be consistent unit-wise, then this would have to be Tesla meters per amp. Okay? So mu naught, like epsilon naught, is a constant used in magnetic phenomena, just like epsilon naught is the constant that we used for electrical phenomena when using SI units. And again, those constants would change should we move to another unit system, but we are pretty much staying explicitly with SI units. Okay, so I'm going to end there, and then I'm going to come back and derive this equation. Okay, awesome. All right, see you guys in a bit. Take care.